Should we make a start? Let's remember what we were doing last week. Okay, so we're thinking about diffusion-driven instability models. And so our basic model is something like this. And VT correspondingly. And we have some suitably chosen initial conditions, I think. And so we can often choose, well, we can choose our boundary conditions, but a choice that we have been making, so this is for x in some domain omega, is for a boundary condition we take zero flux or a Neumann boundary condition. Something like that. Okay, and so by a process of doing some linear stability analysis, what we had gotten down to, if I write them all out on the board, just a minute. Okay, should be that I've got four conditions, essentially, right? So I've got FU plus GV has to be less than 0. 2 FU/GV minus FV/GU has to be greater than 0. And then we get through it. So they all came from looking at requiring linear stability of the spatially homogeneous steady state in the absence of diffusion. And then we had another one, another 2 dV, FU plus DU/GV being greater than 0. And our last one then was dV, FU plus DU/GV being greater than 2 square root of DU/dV into FU/GV minus FV/GU. Bracket. Just check, there might have been a sign wrong, I think, somewhere at the end of the last lecture, so have a quick check on that one. Okay. And so the idea is that these conditions that we've derived here, so the top two, like I said, for stability of the spatially uniform steady states in the absence of diffusion, and the bottom two getting that steady state to become unstable when diffusion is present. So these are necessary conditions in order to be able to find a solution. But if you remember that, strictly speaking, what we also need, and just tuck it in here maybe, is that we need to be able to find a solution, right, of the form, the Laplacian of P plus K squared P equals 0 for x in omega with our boundary conditions. Okay, so effectively in here, the key thing is that we've got these four conditions, we need those. And then we said that that means that we can find some solutions where K squared gives us, so for our lambda, which is a function of K squared, back up a little bit, so that this will give us lambda with positive real part. But we also need to be able to find these K squareds that satisfy this problem. And so what the focus of today's lecture is really going to all be about is trying to understand what values of K we might be able to pick for given problems. Okay. All right. Okay, so in example 1, I think what we're going to do is we're going to go to one dimension. Okay, so sticking with fairly generic coefficients for the moment. So I've got UT, fairly kind of, what's the word? Generic reaction kinetics. So UT is du uxx plus f of u and v, and vt is equal to dv vxx plus g of u and v. Okay. So on the problem sheets, there's plenty of examples with specific u and v, and we'll look at one in a minute as well. So I want x to lie between 0 and L, t greater than 0. here, and I'm going to choose zero flux boundary conditions on the boundary of my domain. Okay. E.g. Neumann. Okay. So what does that mean? It means effectively that ux and vx are equal to 0 for x equals 0 and L. So I guess the first question is really to think about what solutions to this problem look like. Okay, so in 1D, what we're really interested in, okay, so thinking about perturbations about the spatial uniform steady state, and P being essentially the spatial component of that, right, then we're looking for solutions where effectively, think how to write this out, d2p by dx squared plus k squared p is equal to 0. Okay, it's from in here. And we've got these conditions now, dp by dx equals 0 for x equals 0 and L. So if you think about what solutions to this type of problem look like, right, we're going to have solutions where, well, let's write it out. So p of x, is equal to some a, which way around, a cos of kx, let's call it ak for a minute, plus a bk sine of kx. So that's my, just writing down the general solution of this problem, I get something like this. And then if I think about what happens on the boundary, right, I can make further progress. So if I want my dp by dx's to equal 0 at x equals 0. Okay, so when I do dp dx, I'm just going to pull out a sine term here and a cos term there. So the term here isn't going to give me any trouble. That's like 0 on the boundary, but that's going to give me that my bk's then have to be 0. Okay. And then if I think about what's happening at x equals L, right, it tells me that ak times k times the sine of k times L has got to be equal to 0. So that's at x equals L. So this is all very similar to what you did in kind of the first year PDE's course when you looked at the diffusion equation or the heat equation. And so if I want this to be true, effectively that tells me that k has got to be equal to n pi on L. So in other words, the spatial form of my solution has got to look like pk of x is some ak times the cos of, if you like, kx, where k is equal to n pi on L for n is 1, 2, etc. So in general, our AK out here is going to depend on K, but it's going to be independent of X and T, right? So this is essentially the separable solution problem. Okay. So then what does our sort of general separable solution look like, right? So essentially what I have in here, we found all the allowable values of K, then my solution for my perturbation, I was trying to remember what I called it in the lectures before. I didn't give it any name, so never mind, so we'll keep it here. So let's say the general separable solution think we called it W actually, didn't we, for our small perturbation, W of x and t. Right, so if you remember that, so we're summing over all the values of k now that we can get. We've got our ak, we've got e to the lambda, which is a function of k squared times t. And this is the time varying bit of it. And then we've got things that look like cos kx, where essentially in here, this sum is over all the allowable values of k that we can have. So these k's are equal to n pi on L for n equals 1, 2. Okay. Or in other words, if we write this out, we're going to have a sum over n. We've got, let's call it now an, like e to the lambda of n squared pi squared on L squared times t times the cos of n pi x on L. Okay. So can anyone tell me, right, so this is the general form of my perturbation. Can anyone tell me what would happen if instead of having, where have they gone over here, instead of imposing Neumann, so zero flux boundary conditions on my domain, I'd imposed Dirichlet boundary conditions. So I'd held the solution at the steady state, for example, at the boundaries of the domain. Can anyone tell me what might be different about that separable solution? This goes back to sort of first year PDE's course. Yeah.
Well, you just get signs.
You would, exactly. So if we had, instead of here, got Dirichlet boundary conditions, then instead of having cosines, we pull out sines in our solution. Okay, so that's a one to remember. Okay, so what do we expect to happen? We expect that if we start off at a spatially uniform steady state and that these conditions are all satisfied, that if we make a small perturbation to that spatially uniform steady state, then effectively this, then our small perturbation will be governed by, or will look something like this, at least initially whilst those perturbations are remaining small and the nonlinear terms in our equation aren't important. So what do we want to know, right? What we do want to know, I hope, is whether we get patterns in this system. Okay, so that really then becomes a question when it comes to thinking about seeing patterns as to when lambda at these values, n squared pi squared on L squared, have positive real part. So let's think about that for just a minute. Okay, so let's draw a domain here. And so this is going to be k squared. And this is going to be the real part of lambda of k squared. And if you remember that that came from thinking about this quadratic h as a function of k squared. So let's imagine that our lambda plot looks something like this. Okay. Then what I know is that to have solutions to this problem, okay, I can only have the values of k squared, right? So the allowable values for k squared are n pi on L, all squared for n equals 1, 2. Right? And so they're a discrete set of values of k squared. And so essentially they're going to sort of sit along the axis something like, well, increasingly far apart, like this, whatever, right? Okay, so these are the actual sort of allowable values of k squared that I can have. So I'm going to draw a lot, I'm probably going to redraw this plot lots of times. Okay, so this might be sort of pi on L squared, and then I guess this one is going to be 2 pi on L squared, etc. along the axis. Okay. So in this particular context, or the way in which I've drawn it, let's say this one's 3 pi on L all squared, 4 pi on L all squared. Imagine I've put them all in, etc. along the axis. Okay, there are only actually 3 modes that are going to be unstable. Okay, so there are only going to be 3 modes that I see essentially in my initial pattern as it forms. I'm going to see a pattern where I've got n is 3, n is 4, and n is 5. And for all of the rest of the values of n, lambda has got a negative real part. If lambda's got a negative real part, then effectively all of these things will just, those modes will just go to 0. So the only one in my sketch over there that I'm going to pick up is going to be these 3. Okay, so what does that mean? Well, we expect effectively to see, well, what will happen is that these 3 modes will begin to grow in size. And what they will do is they will seed the nonlinear pattern. So what I mean by that is to say that once my small perturbation, which I call W in the lecture notes, once that small perturbation sort of grows, at some point the nonlinear parts of these kinetics will start to kick in and they'll start to play a role. But what I expect to happen is that essentially these modes which grow will seed the pattern in the fully nonlinear case. So I expect to see a pattern at long times that is made up of these ones. And what you often see is, in fact, is the mode that's closest to the peak here. So the mode that grows the fastest, that you are really effective, you often expect to see seed that pattern. Okay, so in this particular context, these are the only 3 that are going to grow, and they will seed the pattern. So we expect to see things that are made up of this. And so just to illustrate then a pattern that was of, let's say this is L of mode 3, and I'm awful at drawing. Okay, so I would expect to see between 0 and L, 1.5, I should have done 4, shouldn't I? Between 0 and L, 1.5 instances of this pattern, whereas with this, I'd expect to see 2 peaks, right? So let me try and draw that for you in a non-disastrous way. So this is the pattern I would expect to see from this in here. So this might be U, for example. Okay, and then I'll try and draw the 3 one, but it'd probably go horribly wrong. All right, so for 3, I've got 1 and then a half. That could be L, couldn't it? There we go. So they're the sort of different kinds of pattern I may expect to see in this system. So under the hood, what's really going on here is the fact that the domain size is playing a critical role, right? So L is present in here. The size of the domain plays a critical role in the patterns that I'm going to see. Okay, can we say a little bit more about that? So what happens, this is k squared again. This is the real part of lambda of k squared. If I have my lambda of k squared looking like this, or it's positive, it's real part, sorry. And in the lecture notes before, I called this k minus squared and k plus squared. So they're just the roots, right? So think of our quadratic h as a function of k squared, then h of k plus or minus squared are equal to 0. That's how they were defined. And you can derive expressions for k plus minus squared from the various combinations of those terms up there. It's all in the notes. So what happens if my domain is very small? Can anyone hazard a guess? Yep, so the domain is really small. What do we think might happen?
No pattern.
No pattern? Yeah, exactly, because...
It's not.
Nothing satisfies their conditions. Well, I could still satisfy those conditions if the domain is really, really small. I'm not too worried about that one. But what happens if this is pi? If the domain is very, very small, I could have pi on L squared over here, right? And if pi on L squared is here, then effectively 2 pi, 3 pi, all of the n pi on L squares are all much further down the axis. Which means that effectively if the domain is too small, I can't find any of my allowable values of k that have a positive, have the real part of lambda being positive, okay? So what's the condition? So effectively, if pi on L squared is greater than k plus squared, implies no pattern, because the real part of lambda is less than 0. Can we fit this in? Yeah. Okay, so the domain size critically influences the patterns that I'm going to see. Okay, and in essence, I'm going to see a bifurcation, right, to possible patterning as I start decreasing the domain size. So as I decrease the domain size till pi on L squared is equal to k plus squared, then eventually that's the bifurcation. Okay. So we have a critical domain size. So L critical is equal to, well, let's just write it this way. Pi on L critical squared is equal to k plus. Okay. All right, so the domain size is critically important, okay? And so as I increase L past L critical, this thing will move in here, and when it does, I'll be able to see a pattern that's just sort of half a wave, if you like. So this one corresponds to something that looks like that would be the pattern with just sort of this one in here. And then as I keep increasing the domain size, what I'll see is eventually more and more of those modes come into this region. And so the pattern that I could see can be more and more complicated. Okay. All right. Let's think about extending our example just a little bit to go into 2D. Example 2. Okay, let's suppose that so now x is xy transpose, so we're in 2D, and I just want to work on a rectangle, so I'm going to have x lying between 0 and Lx, y lies between 0 and Ly, find out my domain. And I want to take the same zero flux boundary conditions. Okay. So I'm solving exactly the same problem as before. It's gone off the board, helpfully. Okay. But if you think about what happens in this context, I get a P, yeah, and I'm going to call it Pnm, Mn of x even, speak today, okay, and so that's going to be an Am n times, and again think back to first year, cos m pi x on Lx times a cosine of n pi y on Ly for nm. Although excluding, I guess, the case where both n and m 0. Let's put excluding. Okay. So you can work through that one, but effectively, again, just solving the same equation. Laplacian of p is 0. So, sorry, Laplacian of p plus k squared p is equal to 0 with n dot grad p equals 0. Okay. So that's what the solution looks like when you have when we're working in 2D. And so again, our general solution, w of x and t, just be equal to the sum over the allowable values of m and n, which we just discussed. What did I call them? A, m, n. E to the lambda of k squared t. Actually, well, let's write this out. Let's write it. K squared t times cos m pi x on Lx cos n pi y on Ly. Okay, and in here now, sorry. Important bit is that our k squared in here is m squared pi squared on Lx squared plus n squared pi squared on Ly squared. Okay. So we've got exactly the same thing as before, except slightly different definition for our k. All right. So I'm going to draw, again, our dispersion relation. So this is a real part of lambda as a function of k squared. Whoops. Looks something like this. And let's begin to think about what patterns on the domain might look like. Okay. So what happens when, for example, we have a domain where the aspect ratio is sort of order 1. So Lx and Ly are on the same kind of spatial scale, and they're fairly large. Can anyone tell me what might happen? Something about over here. Yep.
Would we get a vaguely symmetrical pattern?
Yeah, that's a good way to think about it. So I think what you're trying to say is that I think what you're trying to say is that you could find some values of m and n that weren't both 0, right? Because Lx and Ly are about the same size. So what I hope is that if Lx and Ly are sufficiently large, right, then I hopefully can choose, so for example, if m and n are both 1, that hopefully that points into in here. And then I've got some other points, haven't I, right? I've got one where m equals 2, n equals 1, or vice versa. They'll sit in the same place. And I might have here as well, m equals 2, n equals 2, for example. and vice versa. Okay, so hopefully in those particular cases, the idea is that if Lx and Ly are sufficiently big, I can pick both m and n non-zero and get some values in here. And the values in here are important because they're values where the real part of lambda of k squared is positive. Okay, and if I take Lx and Ly to be really, really big, then effectively the idea is that I might get lots of different values in here that have lambda with a positive real part. Okay, so if Lx and Ly are sufficiently large, I can choose m and n both non-zero with the real part of lambda of k squared, let's call it mn to be clear, greater than 0. So if they're both non-zero, that means I get oscillations in both the x direction and oscillations in the y direction. Okay. And so if I have oscillations in the x direction and the y direction, I'm going to have peaks and troughs in x and y in both directions. And that's going to give me spots or something as resembling spots as a pattern, right? Because they're both oscillating. Let's just say. Okay. So if I've got a domain which is sort of aspect ratio 1 and I pick my domain big enough, then I should be able to see a pattern and it should be spotty. It's going to have variation in both the x and y directions. But now what happens if I choose Ly to be much smaller than Lx, like very small? What? Go back to our dispersion relation plot, something like this. Anyone tell me if Ly is tiny and Lx is a reasonable size, quite big, what might change about my pattern?
Stripes.
Someone say stripes? Can't see who it was, but yeah, cool. Well done. Okay, yeah, so I'm going to see stripes. So what's the problem here? So really what I'm saying is that if Ly is very, very small, right, then so this could be the point where m equals 1 and n equals 1, right? Then so over here, I've got pi squared on Lx squared plus pi squared on Ly squared. Then that's always going to push me to the right-hand side in here, which means that I'm going to have a lambda with a negative real part. And it's all because of this thing being so small that I've kind of nudged over that boundary. Okay. And so that tells me that the only way to get points in here are going to be to take points when n is always 0 and m is not equal to 0. Okay, so there might be several of them in here that satisfy that constraint. So if Lx is sufficiently big, I might be able to choose quite a lot of different points in here so that m is non-zero. And for each one of those, I'm going to have a lambda with a positive real part, which means that I'm going to have stripes. Okay. So if Ly is lots less than Lx, so what did I say? So pi squared on Lx squared plus pi squared on Ly squared is always going to be greater than this k plus squared, if you remember. And it's going to say no oscillations in the y direction which is going to give us stripes as a pattern. Okay. So, short story, if the domain is too small in one of the directions, in one dimension, then effectively the sort of linear, what we're going to see in terms of the linear analysis or predict is that we see the formation of stripes because we can only have oscillations in one direction, and here is x. And then we expect that then that seeds the full nonlinear pattern to form something that's stripy. Okay, so always remembering this is linear stability analysis. This is what happens when there's small perturbations. But generally speaking, what happens with those small perturbations is then realised in the full solution of the problem. On the other hand, if Lx and Ly are both sufficiently large, then we should be able to choose M and N, both not zero, and we should see some kind of spotty pattern. And you can try that for yourself. Okay, so that's why animal coat markings, right? So, and there's some pictures I think in the notes, are sort of consistent with saying that if this was some kind of model for how the markings are generated on the coats of various animals, I think we've got pictures of jaguar or leopards and things like that, then on the body, right, which is a fairly large domain, we might expect to see a spotty pattern, but on the tail, which is effectively a long, narrow domain, right, with periodic boundary conditions in one direction, we might expect to see stripes because there isn't space for those spots to form. And there's some nice examples in there of that. Okay, I thought what we could do for a little bit is then just have a look at some of this in the using Visual PDE. Did anyone try it out? Anyone have a go? Oh, we're both good. Right, let's have a look then. Let me just get this to work. If you've got patterns and you want to come and show us, you can shout out. All right. Hopefully this works. It's on its way, I think. Yeah, okay, shall I make it slightly bigger? Can you read it? Okay. Okay. So we're going to look at the Gera-Meinhardt model, which I can just about see from here. So what's useful about this? So the Gera-Meinhardt model is a really nice example model where, again, like the Schnackenberg model, the reaction kinetics are fairly simple. So you can write down quite easily, if you like, the spatially uniform steady states here. And you can calculate the conditions required for Turing instability. And there's three different simulations that we might work through. And so first of all, what I'm going to do is let's just, what was I going to say, domain. Let's make the domain one-dimensional so we can look at our one-dimensional patterns. And let's change the boundary conditions to be Neumann because we've been playing with those already, I think. Okay. So in here, what you can see, hopefully, over time is the formation of a pattern from a little perturbation. We don't have to wait too long for it to be realised. I think much of the time, yeah, you get an odd number of peaks. I was trying this earlier. So we 1, 2, 3, 4, 5, 6. Is that 7 full peaks and a half peak? Yeah, so that would be an n equals 15 solution on this domain. And you can reset it. And I think you can make perturbations in several places. And sometimes if you do this, you can make it make a slightly different pattern. Although I'm not clearly not going to be able to do that right now. What have we got? 1, 2, 3. So that's something that's similar again. But actually, I think it's flipped its polarity. Okay. And you can do various things within the equation. So I think you can change the diffusion coefficient, for example, restart and sort of see what happens. I think as you gradually decrease the diffusion coefficient, it takes a bit longer to form the pattern. What are we seeing? We've got 6, 7, maybe another. Oh, there we go. Look, we've got an even mode appearing now, right? So we're seeing full cycle 1, 2, 3, 4, 5, 6. Is that 8? I can't count. Okay. So have a go. Think about what happens as you change the the parameters in this domain, and also make some different perturbations. Sometimes when you make different perturbations, you can force it to make different patterns just because you're seeding a different solution. This one takes a little bit of a while to form, but the idea is that if I make a slightly different perturbation to my initial conditions, I'm picking up, there's quite a lot of modes in here I think that are unstable. The ones that I've got a few kind of around the peak in here, I'm picking up some slightly different ones. So this one I think goes very slowly, but we've picked up something that's 1, 2, 3, 4, 5, 6, 7, 8, 9, is that about 10? Okay. And when you want to, you can then go back to, if I can do this, the fully nonlinear case, and you can have a look at its dynamics. One of the interesting things here is that if I just switch it back from 1D to a 2D domain, what it does is copy across the solution that I had before. Okay, and so this is a solution which is just a stripy pattern. And because all it's done is sort of converted that 1D pattern into a 2D pattern in the simplest possible way, okay, that's what I could play with as an initial condition now. Okay, and I'm going to come back to that in just a minute because I'm just going to load the interactive simulation for a brand new simulator where for just a minute, let's put those parameters back to 90 and let's make these boundary conditions to be Neumann again. So if we have a 2D domain and it's the spatially uniform steady state, which this is, and we just make a series of perturbations, it's a bit slow when D is 90 compared to D is 100. But what you can see is what it really wants to do, or what it's going to do, it's going to pick up spotty pattern. Okay, and there's a mixture of modes, I think, that gets left in here because they're not quite regular in space. And they continue to resolve now over time, sort of quite slowly. And one of the things that you can do in this system is you can see that if you try to make a perturbation here in a region which is a trough, the system you can't even see it reacting. And if you make a perturbation in the middle of a spot, then it'll perturb for just a little bit, but then it will come back. Okay, it might move just slightly, but the basic patterns is kept. Now let's go back to this pattern. So it's got the same parameter values and it's generated effectively from a 1D initial condition. And we could ask, is this stable? So if I make a perturbation to one of my stripes, what's going to happen? And one of the nice things about this is then you can see, if you make a perturbation in just the middle of one of these stripes, it initially seeds spots to form along the initial peak. And then you see a propagation of that disturbance out. And so the spots gradually form from the stripes as the initial disturbance reaches them. So in this particular case, okay, we could find a solution which only had variation in the x direction. Okay, so we kind of constructed it by cheating. We found a one-dimensional solution first and just copied it. But then it's not a stable solution in the sense that if we make a little perturbation to it, then it essentially turns into, in this context, a very nice and regular 2D pattern. Okay. So I think there's some quite nice examples in here in terms of the Gera-Meinhardt model. And again, there's a simulation where an example where it starts just from stripes for you to play with if you want to. And then the last one is an example where it shows you that if you just amend these kinetics just a little bit, then effectively what you're doing is providing some saturation in U. So U is going to sort of saturate its own production as U gets large. Then you can get sort of go between sort of spots to sort of more labyrinth patterns. And I haven't tried this yet, so we'll see what sort of happens. So let's make a perturbation. Let me just check the parameter values where it's doing whilst it's doing what it's doing. So K is quite large, and if K is quite large, what did it say it wanted to do? It said, I think it won't form patterns at all. So it's doing something, but it's doing something very, very slowly. And if we decrease the value of K, and you can do this on the fly and let it adjust, you can see quite interesting patterns forming. I'm going to get rid of that so you can all see. It'll form quite nice labyrinth-type patterns. Okay. So play around with this, have a look at what happens to the different types of patterns and understand, or convince yourself, that you're sort of happy with what happens in these different cases. I think the last thing that you can do with this is you can sort of change the domain size in the effective domain size in the y direction, and then you can see how the pattern changes in terms of the number of oscillations you get in each direction. Okay. All right. I think we'll stop there. I encourage you to have a go with this just so that you can kind of sort of understand for yourself the types of patterns that you might see in the system and how they might evolve over time. What we will do next time, or tomorrow even, I think, maybe, is to talk just a little bit about chemotaxis, which can be another mechanism for patterning. Very briefly touch on that, and then we'll think about moving boundaries sort of halfway through tomorrow. Okay, all right, see you tomorrow.